Out in the vastness of space, Earth looks like a serene blue marble, but it's protected by an invisible force field, a magnetic shield that keeps us safe from the harsh radiation of the cosmos. Imagine our surprise, and honestly, our concern, when we found a dent in that armor. NASA and other space agencies around the world are watching this dent with increasing alarm. They call it the South Atlantic Anomaly, or SAA for short. It's a vast region where our planet's magnetic protection is significantly weaker than anywhere else. This isn't just a scientific curiosity, it's a real and present danger to the technology that powers our modern world. This growing worry stems from the fact that the anomaly isn't static, it's on the move. Recent data, confirmed by NASA in 2025, shows that this weak spot is expanding westward, and even more curiously beginning to split into two separate lobes. Think of it like a hole in a shield that is not only getting bigger but also starting to fray into two distinct holes. This intensifies the threat, creating a larger and more complex danger zone for anything passing through it. For NASA, whose job it is to explore space and operate a fleet of sophisticated satellites, understanding this expanding vulnerability has become a top priority. The stakes are incredibly high. Our civilization has become profoundly dependent on a delicate web of satellites orbiting our planet. These orbital assets handle everything from your GPS navigation and daily weather forecasts to global financial transactions and international communications. They are the unsung heroes of the 21st century. But these high-tech marvels are incredibly sensitive to radiation. The South Atlantic Anomaly acts like a cosmic speed bump, a treacherous zone where the normal rules of space weather don't apply. The increased particle bombardment in this area can wreak havoc on sensitive electronics, threatening the very infrastructure we rely on. So, NASA isn't just looking at a map, it's staring at a potential crisis point for our technological age. The anomaly represents a direct challenge to our continued exploration of space and our ability to maintain the complex satellite network that underpins modern life. As we send more astronauts to the International Space Station and plan ambitious missions to the Moon and Mars, we must navigate this hazardous region. The persistent weakening of our magnetic shield in this specific area forces us to ask tough questions about how we protect our assets and our explorers from this invisible yet potent celestial threat. So what exactly is this South Atlantic Anomaly? Let's break it down. Picture Earth's magnetic field as a giant invisible bubble surrounding our planet. This bubble, called the magnetosphere, deflects most of the harmful charged particles blasted from the sun. The SAA is a large region, stretching from the coast of South America across the southern Atlantic Ocean towards Africa, where this bubble has a significant depression. It's not a hole, but rather a place where the field is substantially weaker, allowing the inner Van Allen radiation belt, a zone of trapped energetic particles, to dip much closer to the planet's surface than it does anywhere else. Ordinarily, our magnetic field does a brilliant job of keeping us safe. Generated by the churning molten iron in Earth's outer core, it extends thousands of kilometers into space, creating a protective shield. This field traps high-energy particles from the sun and cosmic rays in two donut-shaped zones called the Van Allen belts. These belts act as a buffer, preventing most of this dangerous radiation from ever reaching the surface or even low Earth orbit. This protection is what has allowed life to flourish on Earth and what enables our sensitive technology to operate safely in space most of the time. But within the SAA, that protection is compromised. Because the magnetic field is weaker there, the inner radiation belt sags downwards, reaching altitudes as low as 200 kilometers. This is precisely the orbit where many satellites, including the Hubble Space Telescope and the International Space Station, spend their time. When these spacecraft fly through the anomaly, they are no longer shielded by the full strength of the magnetosphere. Instead, they are bombarded by a concentrated stream of high-energy protons and other particles that can easily penetrate their metallic hulls and interfere with their delicate internal systems. This exposure isn't trivial. The increased radiation can cause what are known as single-event upsets, basically digital hiccups where a charged particle strikes a microchip and flips a bit from a 0 to a 1, or vice versa. This can lead to corrupted data, malfunctioning commands, or even temporary shutdowns of entire systems. In more severe cases, the constant bombardment can cause permanent damage, leading to short circuits and the premature failure of a satellite. To mitigate this, satellite operators often power down non-essential components when they know their spacecraft will pass through the SAA, a necessary but disruptive precaution. To understand what's causing the South Atlantic anomaly, we have to journey deep into the heart of our planet. The origin story of this magnetic weak spot isn't written in the stars, but in the churning molten metal of Earth's outer core. Our planet's magnetic field is generated by a process called a geodynamo. Think of it as a massive self-sustaining electrical generator. The flow of liquid iron and nickel, driven by the planet's rotation and heat from the solid inner core, creates powerful electrical currents. These currents, in turn, produce the magnetic field that envelops our world. However, this process is not perfectly uniform. The flow of molten metal in the core is turbulent and complex, with swirls and eddies that can cause local variations in the magnetic field we observe at the surface. Scientists believe the SAA is a surface manifestation of one of these deep Earth irregularities. It's not that the field is disappearing, but rather that a localized patch of the field is behaving strangely. Some geophysicists, like NASA's Weijia Kwang, explain that the anomaly is the result of the main dipole field weakening, while a localized field with a reversed polarity grows in the region, effectively canceling out some of the protection. A leading hypothesis for this disturbance points to a colossal continent-sized structure deep within the Earth's mantle. Located about 2,900 kilometers beneath the African continent is a feature known as the African Large Low Shear Velocity Province, or LLSVP. This is an enormous blob of rock that is hotter and denser than the surrounding mantle material. Scientists theorize that this massive formation disturbs the flow of the liquid outer core beneath it. By disrupting the smooth, organized convection of molten iron, it could be the ultimate culprit responsible for creating the weakened magnetic spot we call the SAA. This isn't just a recent phenomenon. While the SAA is currently expanding and shifting, geological studies suggest that this magnetic feature, or something like it, is a recurring event in Earth's history. Research published in 2020 found evidence that the anomaly has existed in some form for as long as 11 million years. This tells us that the SAA is not necessarily a sign of an impending magnetic pole reversal, which is a much rarer and more dramatic global event. Instead, it seems to be a persistent, long-term feature linked to the unique geology deep beneath the southern hemisphere. The continuing evolution of the South Atlantic anomaly has profound implications for our future in space and on Earth. As the anomaly grows and splits, the danger zone for our orbital technology becomes larger and more unpredictable. This is a direct challenge for NASA, the European Space Agency, and a growing number of commercial space companies. Every satellite launched into low Earth orbit must be designed to withstand the increasingly frequent passages through this high radiation zone. This means building more robust radiation-hardened components, which adds to the cost and complexity of space missions and could slow the pace of innovation. Protecting our astronauts is an even greater concern. The International Space Station passes through the edge of the SAA several times a day. While the station has extra shielding in its most frequently occupied modules, astronauts still receive a higher dose of radiation than they would elsewhere in their orbit. As we plan for longer duration missions, including crewed voyages back to the Moon and eventually to Mars, understanding and predicting the behavior of the SAA is critical for ensuring astronaut health and safety. We need better models to forecast the radiation environment and develop more effective mitigation strategies to protect human explorers from its effects. The work of scientists is therefore more crucial than ever. Researchers are using a constellation of satellites, like the ESA's SWARM mission, to continuously map Earth's magnetic field with unprecedented precision. By combining this data with ground-based observations, they are building increasingly sophisticated models to track the SAA's every move. This research helps us understand not only where the anomaly is today, but also where it might be tomorrow. These predictive models are essential tools for satellite operators, allowing them to plan protective shutdowns and maneuver their spacecraft to minimize exposure and prolong their operational lifespan. Ultimately, studying the South Atlantic anomaly is about safeguarding our technological civilization. As our reliance on space-based infrastructure grows, so does our vulnerability to the whims of space weather and deep Earth dynamics. By unraveling the mysteries of the SAA, from its origins in the core to its effects in orbit, we are not just satisfying scientific curiosity. We are actively working to protect the global communication, navigation, and observation systems that are woven into the fabric of modern society. This ongoing vigilance ensures that we can continue to explore the cosmos and reap the benefits of space for generations to come.